Last time we learned about the heap and the wonders of references instead of values. And today we're gonna explore the heap a bit more, or maybe we exploit it a bit. But to do that, let's have a quick look at a certain problem you might encounter during your programming. But let me just quickly write up a program, and of course you don't see that. Why don't you not? There we go. So we have an int a, because we want to store a 5. And then maybe we need another number. We store it in an int b, which is a 10. And then maybe another int c, which is a -1. And then maybe we want to store a fourth number, a d equals maybe just a 0. And then let's do a fifth, e, which is, what's a good number? Let's use 42, that's always a good number. And if I needed any more numbers, I would have to add more declarations for more integers, which is a bit annoying, because oftentimes I have to work with not just one piece of data, but with a large number of different data points, with a huge bulk of data that all has to be processed by itself. So sure, maybe I want to combine all these numbers in a single formula. Like maybe I want to use it in a polynomial somewhere, where all of these values all get combined together, but in a specific way, specific to each individual variable. But sometimes I just have individual values that have no relations to one another. I just need to process them using the same program. Or even if they sort of combine, it can be in a very simple way, just like adding them all up together. If I were to do that now, if I wanted to calculate the sum of all of these values, well, I would have to write that out. A plus B plus C plus D plus E. And I would have to add every further variable into this formula. And if I wanted to change all these values for some reason, wanted to do something interesting with it, well, I would have to write the same formula for each of these values. Let's say I do something simple as multiply everything by -1. I just want to invert all the values. Well, to write a equals, or equal a multiplied equals -1, b multiplied equals -1, and c multiplied. Let's just write it out for the sake of completion, but there's a lot of work to apply the same very simple operation to all of these values. That's a bit inefficient, let's put it that way. And these are just simple examples. Now imagine I have to make a very complex calculation using each individual value. Well, sure, we can outsource all of that into a function or a method, and then just call the same method for each of these variables. That way we don't have to rewrite the same code all the time. We still do have to make this method call all the time. Still not ideal. Wouldn't it be great if we had some way to store all of these individual values, but without providing them a specific name each time that we would constantly have to reuse to use these values? What if you just had a bunch of values, but some other yet undefined way to access them without using the variable names, without using variables in of itself? And of course I'm hinting at something here, I'm not very subtle. We can use what we've learned last time to trick the computer into storing these data points for us without giving them a name. Well, not the same way we've done so far. Let's just remove all of that. Quick reminder. We discussed last time how we have basically two different parts of memory that we use. We have the stack and the heap. And while on the stack we constantly just request a very specific amount of memory space that's used for all our different... What's going on here? I think I lost my connection. This is weird. It's desyncing. Yeah, what's going on? Let's try that again. Sync the tablet. Please connect. Accept. It's showing up. It's not showing up. Why isn't it showing up? I'm sorry, this will take a moment. Technical difficulties. I feel like it wouldn't be another lecture without any technical issues. Let's see, it's... Oh, that's correct. Does it have the right source? Does it have the proper source? It's syncing? Is it synced? Okay, it does. Was it not showing up? There we go. So, but back in the stack. On the stack, we always request a very specific amount of memory that we know beforehand. And that's reserved on the stack for us to use. And whenever we call a method, we would request an additional amount of space. We know exactly how much. We request it on the stack. And if we make another method call, we would request another piece of memory. And once the method returns, we always free that amount of memory that we requested and go back one level lower or higher up on the stack. And then once that method returns, we go back up one. And so the stack is always filled from the top down, full of data, only as long as we need it, and as soon as we don't need it anymore, we free all of that. So stack is always filled up at the top completely, and only as long as we need the data. The heap was different. In here we request a certain amount of data, but that data could be reserved anywhere in here. Well, it tends to be located in one cluster, so as to leave the free space as large and continuous as possible. Technically, we could receive data in here, or maybe up here, like the top, maybe down here. We don't really have much control over that. We just get memory that we just decide we need now, and in that moment we reserve space somewhere on the heap where there's free space, and that's what we use. And once we don't use that anymore, that memory is still blocked until the garbage collector works in the background and decides, yeah, this is not used anymore. We can't free that permanently. What that means is that in our program, when we have to store a bunch of data, we could use the stack, as we did before with the 5 variables. But we would need to explicitly tell the system, hey, reserve us 5 different memory slots for an integer, and refer to them using the names A, B, C, D, and E. Alternatively, we can use the heap to store the data. And we can tell the system to just reserve space for our integer. And here comes the interesting part. Let's start with that. How do we reserve space for an integer on the heap? We have to use a class, because classes are data that's stored on the heap, while structs, the one we learned first, is something that we usually store on the stack. You can have it on the heap as well, but we don't discuss that yet. We'll get to that maybe in a second. First, let's write a simple class. Let's call it storage. And this class still has no proper curly brackets. Let's rectify that. It's not gonna get any better. Let's leave it like that. And it's storing a simple integer value like that. Then make a constructor. Force of habit, we're not there yet. Storage. Lowercase value, so we don't mix up the names. And we assign value to value. We assign lowercase value, the argument we got through the constructor method, to the uppercase value, which is the internal field of our storage class. And we leave it like that for now. So when I write a program, create a new storage A, let's use A again, because I'm lazy like that, a programmer after all. And we're calling the constructor method storage. We'll give it the 5 we did earlier for the A. At this point, it will reserve space for a storage on the heap somewhere. We have no control over where. We just know it's gonna be on the heap. And we're assigning the address of that storage to the variable A. So keep in mind, A is not gonna store the data itself that we have defined here, this 5. It's only gonna contain the address in memory, in the heap, where our storage is located. So when we access a.value for something, using the dot operator, this only means go to the address that's stored in A and use it, or assume this part of the memory you're going to is a storage. So when I say dot value, it knows, okay, look for the integer that's stored at that address that we have stored in A. Like here, this might be our A. We have the int A. This int value, well, whatever, 5. And up here we would have, let's clear that out a bit. It's not pretty, but it should get the job done. Stack. And somewhere in here we have the storage A, some mystery value which points to this address in heap. Oop. That's what we have so far. Now one thing we can do is expand our storage a bit. And depending on who you are, this might blow your mind or just bore you to death. But it's a pretty cool feature of many languages, by the way. It's not exclusive to C#. This is a pretty common concept we're talking about right here. And what we can do is we store another storage. Storage. We'll just call it other for now. And let's expand this a bit. Like, technically I don't need to do this, but just for completion's sake, to make it clear that what we intend to do here. That equals null. Just to make sure that by default this field other will contain a reference to the address 0. So while our A has an actual address somewhere in memory, by default this field other will have value of 0, which means it has no address it points to. Like, there is no object we can refer to yet. So we have to expand this a bit. We have another storage, other, which has so far nothing, pointing nowhere. But now we can use a.other and create a new object in here. This is where the fun begins. What I did now is assign to this little space in memory other, the field other of our initial object A. This is where we now have an actual reference to somewhere in memory. And where does it lead to? Well, to another storage. This is an int value 10. And this is storage other. This one doesn't have any, because we only cited the value 10, no reference, but this one now has some mystery value which points to this storage. So our variable A exists up here on the stack. We explicitly told the system we have a variable A now. But then from A we were able to reference a second object that has no direct name up here, but we can still refer to it using A. And then we can go a step further and make a.other equals new storage -1. And that means we just expanded on this one. And maybe the address is right after this. And now we have a new one here. I'm just not gonna fill out these. -1. That's the next object. So we only have one actual variable that we declared, A, but we have 3 different objects with 3 different integer values we can now refer to. And as you've noticed, we can just expand on this as many times as we want. As long as there's storage space available on Heap, we can just set other in the newest object we created to another new object we create at that moment. So the amount of space we use using this variable A is not fixed in place. If we just set storage to a struct and just stored the integer value, we know exactly, okay, this A will take as much space as a storage struct will need, which has only one integer, so we only need space for one integer. That's all the space A is gonna ever use. But by turning this into a class instead of a struct, we now skip to the heap, where the size doesn't matter anymore. We can just tell it to store an integer as before, but we can tell it to also store the address, only the address of another object. So this one storage instance only stores one integer and one reference to another storage. But by adding more storages, we can change them, we can chain them together, which means we can reference as much memory as we want, all from this one variable A. Of course, writing .other is not much better than writing A, B, C, D, E all the time. So you wouldn't write it out like this. Instead, what we can do is we can make a little step here in between, and let's take, actually let's skip this one as well. We're gonna make a second storage we're just gonna keep A as the original, but we're gonna take T for temp, and we're gonna set it to A. Now what happens here? If this was not a storage, but something like an integer or even a struct, we would set the value of A to T. So we have now another storage, T, and we copy the value from the original A to this new variable T. We copy the content of the memory that we store for A. If it was an integer A, we would just copy the integer value, and we have now twice on the stack. But storage is a class, so what we're storing here is an address. So while they both have the same value here on the stack, it's just the address, and they both refer to the exact same memory in the heap, the exact same instance of storage. So if I use a.other or t.other, in both cases we refer to this other down here, this specific point in memory. A.other is effectively the same as t.other. So if I set t.other now to new storage, I still get this instance with a 10, and now I can set t.other. And what I did now is I changed the value up here on our stack to store the same value as we did here. We created a new other. Sorry, not here. Here. We copied the value from this memory part onto the stack here. And that means that A still references this part in memory. But our T now points to this one down here. And so when I say t.other now and assign a new storage, it will actually change this value, not up here anymore. And I can set t to t.other. And we change this value up here again. A still points to the first one here, but T now points to this last one down here with the value -1. And so I can keep going with t.other equals new structure, and then I just set T to t.other. I can just repeat these exact two lines here, and as many times as I repeat them, I would just add new storage instances to the memory, storing -1. And repeated means we can use a loop. So instead of doing this, let me just move this up a bit. Let's put it up here. Let's keep that as a given, and we expand from there. We can use a simple loop like for and I equals. Now let's do it like this, equals 10. Repeat it as long as I less than 20, and we increment I in each step. And what we're going to do is we're setting t.other to a new structure, a new storage, not structure, storage, I, and then setting t.other. And I'm gonna remove this now, because that's not gonna help us anymore. But what we have now, let's a line in between here, separator, is we create 10 new storage instances, each with a different value, from 10 to 19. And they're now all accessible to us just through the variable a. We can just use a.other, but we can just call a.value to get our initial 5, or a.other.value to get the first storage we created in the loop with a 10, or a.other.other to get 11. Or of course we can use a loop. Let's move on to the next page maybe for that. So let's say we have our initial a. Just a reminder. A is the original storage. We can do a little while loop. This time we don't know exactly ahead of time how many times we're gonna run the loop, like before. Here I knew exactly I want to run it 10 times, from 10 to including 19, to create new storage objects. But if we just give them a and we're told, hey, this is a storage, we don't yet know how long the tail is gonna be. How many storage instances are actually in this chain. But we're gonna start with a, and we're gonna start off with a storage. Let's use a different name this time. Let's use C for current. Actually, let's just write it out, current. It's equal to a.other. And now we can write a loop while current not equals to null. Remember last time, null is a special keyword in C# to indicate that a reference points to nothing, points to the memory address 0, meaning there is no object it refers to, there is no point in memory this points to actually. Right, so the default value you would have with other that we specifically set here, we're going to check for that now, which we can do with a not equals. Not always the best solution. Depending on the scenario, there's a better way to check for this, but for us right now it's enough. We're just going to pretend we're comparing the actual value that's stored in current, which is an address value, and we compare it to null, which is just 0. But specific for classes, for reference types. And if it's not null, then we can have an actual storage instance that is chained onto a. Keep in mind, current is right now the other field of our a. So original a with the value of 10. Oh no, that was a value of 5. And actually, no, let's write this down a bit differently. So we have our original a, which points to 5. And this 5 might point to nothing, 0, but in our case it points to 10. Which itself points to an 11. Which then points to 12, because we created all of them earlier using the loop. Until at some point we hit, let's make this a bit, ... until we hit finally the one with the 19, the last one, which points to nothing. 0. Now. So right now, current is a.other. So whatever this reference is, this address, we store it in current. So if current is not pointing to 0, if it's not pointing to 0 in here in A, then we can just take current and store current.other and repeat the loop. This is not doing anything right now except taking the next address, pointing that in, copying that in current, then checking if current is now 0, so if it's pointing to nothing, and if it's pointing to an actual object, then we're gonna take that value, that address, copy it in current, check if it's pointing somewhere, and if it does, then take the address from that somewhere, and we're gonna keep that up until we hit this point here, where we store this null reference. That's what I'm gonna call that, because it's a reference set to null. It's pointing to 0. In which case, this loop is gonna stop, because now current is equal to 0, to null. And so the loop stops. That means in this loop, we're gonna look at each of these storage instances exactly once. And we can do stuff with that. Like sum. And we're gonna start maybe with a.value. So the original value in A, which was 5. And then we're gonna run through all these different storage instances that are changed into that. And we're gonna take the sum. And we're gonna add the value of the current storage we're looking at. We add it to the sum. And then we're gonna advance our cursor, so to speak. If you imagine it like a text cursor where you're just looking at this one, then you move one to the side, next letter, next letter, next letter. You're always marking down where in this chain of storage instances we currently are. And that's our current. I'm gonna advance current to the next one. No. Other. Right. And so by the end of this, we're gonna have a sum. That's the sum of all the individual values we stored before. And all without having more variables than just A, T, and current. Well, and sum. But we didn't need an A, B, C, D, E, F, G, H, and so on. All of the data is stored on the heap without us knowing ahead of time how much space we are actually going to use. Like, the computer will not know how much space it will eventually request on the heap. It will just tell us if the heap doesn't have any more memory and your computer program will crash. Not the computer, just the program. unless you deal with that. Different topic for quite a bit later in our lessons. What we've done here has a specific name. Like, this is a very primitive implementation of it, but it's called a linked list. We have a list of instances that are linked together by themselves. Each individual element in our list is one storage unit that points to the next storage in the chain. And specifically in our case, we're pointing to just the next one. So usually you would have, instead of other, you would just call this maybe next. And actually, you can go a bit further, and some lists are equipped with another reference to the previous one. These are a bit more complex. You have to always, when you create a new storage instance, you have to provide a reference to the previous instance. But that's perfectly fine. And you always have the advantage that instead of just moving forward like we did here, where I could only start at one point and go to the next one further down on the list, if you have a previous, you can also go back up, which is very useful. And linked lists are a very useful tool. Like, the specifics of how they are assembled and how they're used changes over time. There are even kind of linked lists that don't even use class, that kind of go around the whole heap thing, sort of, not really. But the basic idea is just that during runtime you request a specific part of memory, and this part of memory then references to another part of memory that you request during runtime, which then points to another part of memory, and lets you dynamically expand the amount of memory you use and shrink it again dynamically. Very useful structure, data structure. But for us, this might be a bit overkill. All I wanted to do was store 5 different integers without writing out individual names for each value. I just wanted to be able to use them all. Also, I didn't want to write the same piece of code again and again and again just because I have to redo it, but with a different variable name. And for cases like that, there is another very important data structure. That's not really data structure so much as actually a fundamental type that exists in C#. And it's technically a class, but it's a bit weird. It's gonna be different from what we've seen so far. I'm gonna write something out here. We'll talk about that in a minute. This is declaring a new variable with a specific type, which is not integer. Integer is involved, but this entire thing is the type, including these square brackets. These are important. And here we initialize the value. And as you can see with the new, we're creating an instance of a class. This is a constructor. It looks a bit different, but it is a constructor basically. The new keyword is the important part you have to look out for. Also again, square brackets, not curly brackets, not round brackets, normal ones, just square brackets. C# uses all the brackets. What we're doing here is reserving space in our heap. Keep in mind, new keyword, this is a reference type, a class. So we are reserving space on memory using this. Well, okay, structs are also a new keyword that was badly phrased, but this is a reference type. We're reserving space on heap for exactly 5 entries of this type in front. This type here. So usually I would just write out int a, it's 5. I'm reserving space on the stack for exactly 1 integer. By writing it out like this, however, I'm reserving space on the heap for exactly 5 integers. This thing is called an array. Just a heads up, I'm used to calling it array. Basically, the German pronunciation would look at that word and think, oh, there are 2 R's, so the A is shortened, so it's an array. I'm pretty sure it's array. I'm gonna jump back and forth, I'm sorry. This is gonna annoy you, I know it. You'll have to live with it. And you can turn any data type you have into an array. All this does is say that whatever type you write in front here, don't just store one of this, store as many as we define back here. So right now we defined our A to be an array of integers with 5 elements. And we can access those 5 different elements by using these square brackets again. I can, if it's just a normal integer, I would just say A equals 10, right? But this is now an array. This is not just one value anymore, this is 5 integer values. So I have to now specify which of these 5 I want to change. Sorry, that's the wrong code. I use these square brackets now and give it an index. We start with 0, set that to 10. Then I can give it another index 1 and set that to -1. For example, and 2, it looks like a J, I should take more time with that, 5. That way I can write data into our array and I can reuse that like a variable. Basically this replaces our A we had before, this could replace our B, this replaces our C. So it's a bit more to write, but we can use it just like a normal variable before. Just instead of the variable name, we have the initial variable name and the index, which is the position in our array. Because we requested space for 5 integers. That means we can address 5 different positions in the entire block of memory that we requested for A. We requested space for 5 integers. And it's gonna reserve that space in one continuous chunk of memory. There are gonna be no spaces in between. It's one large 5 integer long chunk of memory stored on the heap. And so if we want to get the different values inside this block, we have to start from the first position, position 0, which is what A actually points to. And then we have to tell it to go 1 integer further, or go 2 elements down, a third integer. Also keep in mind just that like we had with our made up CPU right in the beginning in the first lessons, we always start at 0, index 0. Think of it this way, A points to the very first integer in this entire block of 5 integers. So we're gonna start at A with no moving ahead. But when we want to get the second element, well, we go to A and advance by 1. If we want the third value, we go to A, the first value, and advance by 2 to get to the third. So first position is index 0. Second position is index 1. And actually, this is so effective, it's so simple, because internally the computer just has to add a 1 to the actual address value in memory. Like, remember, A is now a reference to a piece of memory somewhere in the heap. So this is just gonna have a number, which is a memory address. And we're just gonna add this value, this index, to that memory address, and we automatically get the actual memory address for that specific integer we're interested in. Arrays are just a slightly fancier way to directly manipulate memory addresses to get around having to store individual memory addresses in dedicated variables. And now that we have this construct, which just lets us use integer values to refer to different parts of memory, we can use our old friend, the for loop again. Alright. I'm gonna start at 0. We're gonna run down until we're hitting 5, because we have 5 addresses. You mind, this loop will run only as long as I is less than 5. So it will run up to including 4, but we're starting the index at 0, so 4 is actually the 5th entry. Right? Remember that. Index 4 is the 5th and last entry. 5 would be the 6th, whatever, entry, which doesn't exist. We only have 5. So start at 0 and go to less than what actual number of elements we have. It's always going to look like this. If you see a for loop and they're using arrays, you can immediately tell, okay, it's going to have 5 elements, so this is something less than 5. It's pretty convenient. At some point you just look at this line and you blend out everything else, you just look at this number, okay, 5 elements, done. Because this is a very, very common piece of code I'm writing here. And you can do some fun stuff. You can, of course, use the values if you want to, but you can also just write values if you want to, like this. This would fill all 5 positions in our array with the values 0 to 4. And instead of doing this, I can, of course, go back to our initial problem, go to the sum, if we wanted that. I'm gonna start at, let's just start at 0, and then sum plus equals a at index I, and done. And that's how we are now summing up all the values we have stored. This time not as a linked list, but as an array. Arrays have some advantages over linked lists and some disadvantages. First of all, arrays are a very efficient way to use memory. There's no overhead, you tell the system directly, hey, we're reserving memory for exactly this many integers. And you just pack them as tightly together as you can. The only overhead we have is for storing the initial first address where our block starts, in A. But everything else is calculated as needed as you go. So as terms of memory, very efficient way to deal with that, and addressing these individual values is also very easy and very quick for each position. We can immediately go to the 3rd entry with just the index 2. We can immediately get to any value in our array by just knowing the position of it. With a linked list, well, the memory is scattered all over the heap, because we're constantly just telling the computer, now I need 1 additional space for storage, for example. And now I need another piece of memory for storage. And so it has to constantly find new free memory in our heap, which can be all over the place. And instances of objects do have some overhead, because the computer has to keep track of what is an object, where is it stored, what are these properties it has. And that adds a bit of extra memory. Not much, you shouldn't have to worry about that. I mean, there are limits, of course, but technically it exists. It technically adds a bit of overhead. Plus, you constantly have to look up a specific part in memory to read an address, to jump to the next part in memory, to read another address, to jump to the next part in address, to read another piece of memory, and that's the only way you can get through the linked list. I don't have a convenient way to just directly go to the specific position I want. I have to start at the very first one and slowly iterate through the list, as we did earlier. Or maybe I start at the end and go backwards if I have a bidirectional list, but that's the downside. On the positives, a linked list does not give you a fixed length. You can just add more items as you need them. This array has to be declared upfront with 5 elements. We have to reserve the space we need, and that happens only once. So if we now suddenly have to add a 6th number, well, doesn't work. There's no space for it. We have to create a new array if we want that. And let's look at that, because we can learn about specific value. Keep in mind, this integer array is a class. And classes can have methods and fields that we can use to extract data from them with the dot operator. And we didn't create this class, it comes built into C#, into the language. But we do have methods on here and fields that we can access to get data. So let's make another one. Let's call it B. This is going to be also a new integer array. But this one is going to be exactly 1 larger than A, because we want to store another value in the end. And I could just write out 6, of course, but let's pretend I don't know how the original array was. Maybe we got A through a method. Or maybe I'm using the same code in a method that's used for different arrays. See, I'm not gonna get rid of that habit. Well, what we can do is we refer to our A and use the dot operator to access a field called length. Which is an integer value that contains this 5. In fact, usually if you write a for loop like this, you're not actually using the 5. You would also use a dot length. So this loop will work no matter how large this array is. I could just set this to 3 now. I mean, we only set 3 values anyway, and this loop will work. And I can just extend this to 5 and the same loop will still work. It's always going to work exactly from the first to the last element. And this would now go to exactly the same length as A. So we're just gonna +1 this. And we're done. This array B will have exactly the same number of elements as A plus 1 extra. Now we can go through a loop again. And I'm lazy, so I'm not gonna bother writing that out. I'm just gonna copy this. That plus I, and what we're going to do here is we're just going to write out B I equals AI. For every index in the original A, we're going to copy that value into the same position, the same index in B. And now we can go to B. Actually, let's make something fancy. We're going to take B, then we're going to take B.length minus 1. And we're going to plus equals that EI. So what we did here is copy all the old values from our original A into the new array B, and filled the last spot with the sum of all the values. So A is just 1, 2, 3 right now. Or actually, sorry, we filled it up here, so it's 0, 1, 2. And B is now 0, 1, 2, 3, which is not very convincing. So let's I didn't fill it up because I had some. Okay, never mind. Let's just erase all of that. So our A actually is 10, -1, 5. Continuous block of memory containing these 3 integers. And B is continuous part of memory containing these 4 integers. And 14. Why did I use length -1? Well, keep in mind, length is the amount of elements, but we always start counting at 0. So for length of 1, the last element is going to be 0. For length of 2, the last element is going to have index of 1. Length of 3, last element is going to be index 2. So you always take the length and then subtract 1 to get the index of the last element. Instead of this, we could of course go bit for optimization and just use a.length, which we already know is exactly 1 less than the length of b. And here, well, we could also go for a, doesn't matter. I'm just choosing b to make it clearer that we are counting the numbers of b and that there's no other interaction with a. Also important, I'm going towards the length of a up here because I'm copying over the values for a. If I were to go for b, then we actually would have a situation where we check the index 3 for b, or want to fill the index 3 for b, but a doesn't have an index 3, it only has an index 2 at most. So that's why it's important to use a. Copying from the source to a larger target. Those are some basics for arrays. Let me give you one last mind screwing. This is an array of integers. So we have the original data type and we declare this an array. Right? Data type added 2 square brackets. Now it's an array storing that initial data type. Well, if this whole thing now is a reference type, that means we can add another set of square brackets behind this, right? So this is now the data type we store, and we store it as a large chunk of memory of several of these. We have now an array filled with arrays filled with integers. An array of arrays. This is a legitimate construct you will see at some points. So we can make it another new int array. Actually, let's do it like, let's just do so, just to make it simple. We can create an array of arrays where our first array that we actually have in A is going to contain 2 elements, and each of these elements is another array of integers. Remember, this is a reference type, so our A is actually just storing a single value, just a memory address. So this A here, it's also just going to store a single memory address to a block of memory that contains 2 individual values, which in of itself are further memory addresses 2 blocks of memory storing integers. Now here's where we have to keep attention to references and null. If I create an array, like maybe with more elements that I actually assign, well, what value is A3 gonna have? The logic is the same as with structs. If I don't specify anything in the constructor, it's gonna fill the memory region with a value of 0. So just the value of 0 for integer, A3 would have now 0. And if it's a reference, well, 0 just meant null. Integer array, that's a reference. So we're gonna point to a part of memory with 2 values, which are both null references right now. To use them effectively, we would have to first go to the first address, index 0, and also call the constructor to create a new chunk of memory here, which maybe 3, and A1. It's gonna be another integer, but with just 1 element. Not necessarily useful, but possible. You can also create an array that has just 0 elements. That is perfectly valid. And sometimes it's useful, but that's specific parts in programming that don't come up too often. Actually, they do come up often enough that there is a yeah, okay, that comes up often enough, but that's more about handling default values and avoiding null references and error handling. Doesn't matter right now. But now we have, let's write this down a different way. A is now a chunk of memory containing 2 references, 0 and 1, and they each refer to another chunk of memory, which contains values. Oh, okay, that didn't work. Let's try that again. Oh, A points to somewhere in memory. Let's write this out properly. That contains 2 further addresses that point to somewhere in memory where we have a block of 3 integers, this one, and one with just 1 integer, this one. And so when I want to get to one of those values, I would have to go for A0, 0, 1, and maybe A0, 1, and so on. So I would always address which address I'm going towards in the first array and then which in the second array. And of course I can make an array of arrays of arrays of arrays of arrays. I can stack this infinitely. Because every time we write this out, we created a new type, or we use it as a new type, which itself can be an array. Right? You have to just keep attention to this being several different arrays in memory. So even though it all comes from this one variable A, well, I can have one last array in the end with a length of 3 and one with a length of 1. This is perfectly valid. And that can sometimes mess things up, depending on what you're designing. Let's say I wanted to have a matrix, just a 2-dimensional matrix. Well, I could use 3 in here and 3 in there, but only 1 in here. That doesn't work. Actually, I would also need another here. Like that. So maybe those are the rows and these are the columns, or these are the columns and these are the rows. Whatever. This would not be a fully functional matrix anymore. because one of the columns or rows, depending on which order you personally choose to write this out as, there's only one element where there should be 3. So for cases like that, there's a special construct for arrays. You can write this out with square brackets again, but now I put a comma in here. Just to clarify, I'm striking this out to not confuse the code, but to still see it. This is valid programming that's useful in many cases. You can also find it under the term jagged arrays. Because it's not all nice and symmetrical, we have some asymmetries in here. This is a perfect matrix though. Write it out as new int 3, 3. And that's it. Difference is now that we have initialized it with, hey, this is a matrix, this is a multidimensional array, 2-dimensional in this specific case, I have to use a comma everywhere. So I have to use 0, 0, it's 1, or 2, 1, like this. So instead of 1 index, now you always have 2 indices. This is specific for case where you want to make sure that it's a continuous chunk of memory and I have all the data I want for a matrix, 2 dimensions, or maybe a 3-dimensional array. Could also do that, or 4-dimensional, whatever you need. In the end, this is only going to flatten this out into one continuous chunk of memory. So if we think of a matrix like this, well, in memory, it's just going to write it down as 2, 3. And it's just going to know, hey, this is first row, this is second row. It's just some calculations the computer is going to do in the background when you write this out. But in the end, effectively, it's still just going to write one large 1-dimensional array, a very basic array, and it's just doing some math to skip the indices back and forth a bit to make life easier. Okay, we got that, we had that. Anything I wanted to go over? We had the linked lists, we had the arrays, what did I forget? I feel like I wanted to address something important. I can't remember what it was. Give me a second. No, that is not today. Get length. Oh, that doesn't matter. Let's cover that. No, I think actually we're done. If not, I'm just gonna include it in the next one. Yeah, that's some methods of using the properties of the heap to our advantage to store data without specifically addressing each one through a variable name. Also a convenient way to step through the data. Since if we don't have to use variable names and just have arbitrary values that we can calculate on the computer handle, like indices, we can have automated functions that work through all the data at once. So our original problem with summing stuff up or changing every single value in its own way can be handled in these ways. Also, we got some more practice using classes. Okay, I think next time we're gonna look at some additional properties of classes, and then we're ready for the big league. So congrats. This was second to last lesson. If you made it this far, you are only one lesson away from actually writing your first program, which definitely I'm gonna tease you out for in 2 lessons. Homework today, that was what I forgot. The homework. Okay, we're gonna make it this simple. I demonstrated to you just now matrix in C#, special version of the array. And I demonstrated that you can implement the matrix as just a linear sequence of numbers. We just skip ahead in between. Like this and this is the same. It's just arranged differently in memory, but you can use it like this. That's not a problem. I want you to recreate this effect using just a single array. So I want you to have, let's use a class, matrix, whatever, and it's gonna have a constructor that gets two values, and m and n. I'm not going to write out the rest. And this is going to define the size of the matrix. And I want to have one method get value. And x. Actually, x and y might not be. Let's use a and b. Well, I and j would be more classic, right? It's I and j. Why did I mess up my letters again? Oh yeah, right. Int that. And void set value. Just gonna get the int I and j int b for value. And all of that has to store internally using just a singular regular array. Let's call it values. So we have one constructor that just accepts these two integers to determine the size of our matrix. We have one method getValue that receives coordinates and gives us the integer value at that position, and a second method setValue that gets another set of coordinates and a value and writes that. And all you have to work with internally is a singular normal array values. I want you to figure out how that can be done using all that you've learned today. And with that, I'm going to leave you. Until next time. Bye-bye.